In the beginning, there was only fire, a furnace so dense and blinding that time itself seemed crushed beneath its weight. The newborn universe burned with a heat beyond imagination, a storm of light and matter tangled so tightly together that nothing could escape, no photon could wander free, no glimmer could break the shroud. Then came the great cooling. The fire dimmed just enough for atoms to take shape, for electrons to settle into orbit around protons, and for the first time, light was released from its prison. It was not a blaze, but a whisper, a gentle sigh left drifting through space as the universe exhaled its first breath. That whisper has never stopped. It moves still across the darkness, stretching thinner with every expansion of the cosmos. Its frequency slowed to the soft glow of microwaves, its message carried across more than 13 billion years of time. It is called the cosmic microwave background, a relic older than the stars, a veil of ancient light that blankets the entire sky. It looks faint, uniform, featureless, and yet within its delicate variations lies the memory of creation itself. Every galaxy, every star, every world was seeded from the ripples written in this ancient afterglow. To some, it seems like static. Like noise to others, it is the single most important message the cosmos has ever delivered. The universe does not often speak, but in this faint whisper, it left behind its oldest truth. The question that remains is whether humanity is yet ready to understand what those whispers are trying to say. In the middle of the 20th century, the world stood at a threshold of silence and discovery. The Second World War had left behind not only scars but also tools of listening, great machines once built for military communication that were now reimagined for the cosmos. One of these instruments stood in Holmdel, New Jersey, a towering horn-shaped antenna designed to catch the faintest signals that passed unseen across the sky. It was here, in 1965, that two radio astronomers, Arno Penzias and Robert Wilson, found themselves listening to a sound they could not explain. Their task had seemed straightforward. The Bell Telephone Laboratories had built the massive antenna to test communications. By bouncing signals off satellites, Penzias and Wilson were repurposing it for astronomy, trying to measure faint radio waves from the Milky Way. But instead of silence, they encountered a soft, persistent hiss, a background noise that would not leave. The hiss was stubborn. It remained whether the antenna was pointed toward the center of the galaxy or away from it. It stayed at dawn and at midnight, in winter and in summer. No matter how carefully they adjusted, no matter what direction they turned, the signal clung to every observation, a veil of static that resisted all attempts at dismissal. At first, they suspected interference. Perhaps the nearby metropolis of New York was bleeding radio signals into their instrument. Perhaps military radar was intruding. Yet none of these possibilities survived scrutiny. The hiss was everywhere, unchanging, as if woven into the very fabric of space. They searched for earthly flaws. The antenna's electronics were dismantled and rebuilt, yet the noise persisted. Even the pigeons that had nested inside the great horn, leaving behind a layer of droppings that the scientists delicately referred to as a white dielectric material, were evicted. Still, the sound remained, faint but immovable. In their frustration lay a paradox. Noise is usually dismissed, discarded as unwanted clutter in the search for signal. Yet here, the noise refused to vanish. It demanded recognition. It was as though the universe itself was whispering into their instrument, and the only question left was whether humanity would listen. What Penzias and Wilson did not know was that 30 miles away, at Princeton University, a group of physicists led by Robert Dick and Jim Peebles were preparing to search for exactly such a signal. For years, theorists had suggested that if the universe had truly begun in a hot, dense state, a Big Bang, then the afterglow of that primordial fireball must still linger. It would have cooled over billions of years, its light stretched by cosmic expansion, until it faded into the microwave spectrum. It would appear today as a faint, uniform glow filling all of space, a relic not of stars or galaxies, but of the universe itself being born. The idea had roots stretching back even further. In the 1940s, George Gamow, Ralph Alpher, and Robert Herman had calculated that the Big Bang should leave behind such radiation. But their predictions went largely unnoticed, buried beneath other debates, dismissed by many who favored a different vision of the cosmos, the steady-state model, where the universe had neither beginning nor end, expanding but eternally replenishing itself with new matter. If the steady state was true, then no echo of creation should remain. And yet, in 1965, the whisper was there, unmistakable, undeniable, unrelenting. The noise that Penzias and Wilson struggled to eliminate was the very signal Dickey's group was building instruments to find. When the two groups became aware of each other's work, history pivoted. Penzias and Wilson had no theoretical framework to interpret the signal, but their measurements were precise and careful. Dickey and Peebles had the theory, the expectation of a cosmic relic, but they lacked the data. Together, the puzzle completed itself. The noise was not noise at all. It was the afterglow of the birth of time. News of the discovery spread quickly, and with it, a seismic shift in cosmology. The cosmic microwave background became the smoking gun of the Big Bang. The steady-state model, elegant but fragile, could no longer stand. The universe had a beginning, and that beginning had left behind a trace. Everywhere one pointed a radio antenna, the glow of creation poured down, faint but eternal. The philosophical weight was immense. For centuries, human beings had stared into the night sky and wondered if the cosmos had always been, if the stars were eternal lanterns, or if there had been a first spark. The whisper captured by Penzias and Wilson answered in its own way. Yes, there had been a beginning. Yes, time itself had opened with fire. And yes, even now, that first moment still speaks across the abyss. What makes the discovery so haunting is not only its confirmation of theory, but its intimacy. The photons captured in their horn antenna were ancient travelers, released when the universe was barely 380,000 years old. Before that epoch, matter and light were bound together in a dense fog of plasma. Photons could not travel freely, scattering endlessly from electrons and protons, but as the universe cooled, atoms formed and the fog lifted. The first light burst free, setting out on a journey that would last more than 13 billion years. Some of those photons fell at last into the horn of an antenna in New Jersey. Each photon was a messenger from the edge of time. Each carried with it a fragment of the infant cosmos. Together, they wove a tapestry of the early universe, a fabric of subtle ripples and fluctuations that would one day grow into galaxies, stars, and worlds. To listen to the cosmic microwave background was to hold a baby photograph of existence itself. Yet in 1965, all of this lay just beyond immediate reach. The discovery was raw, its meaning vast but still emerging. Scientists understood that they were listening to the echo of the Big Bang, but they had yet to decode its details, to map its patterns, to extract from its faint uniformity the secrets of cosmic structure that work would come later. Through satellites and careful measurements, through decades of refinement. But in that first moment, what mattered most was recognition. The universe had left a trace of its birth, and against all odds, humanity had stumbled upon it. For Penzias and Wilson, there was a humility in the discovery. They had not set out to prove the Big Bang. They had been searching for silence, for clarity in their instrument, and instead, they found the loudest silence of all, the voice of the cosmos speaking from the dawn of time. It was a reminder that the greatest discoveries often arrive not through conquest, but through attention, through listening to what refuses to be ignored. The cosmic microwave background would soon be called the greatest discovery in the history of cosmology. A turning point that shifted speculation into certainty. It was no longer possible to imagine the universe without a beginning. The whisper had spoken, and it could not be unheard. From that moment onward, astronomy would never again be only about stars and galaxies. It would also be about echoes, about listening not to what shines now, but to what once burned long before the first star ignited. The sky was no longer silent. It was filled with memory, and the memory was older than time, as humans had ever understood it. The discovery of the cosmic microwave background was the discovery of history itself, etched in radiation that bathes every corner of existence. It is still with us now, still falling quietly upon the earth, a perpetual rain of ancient light. Every radio telescope that lifts its gaze into the heavens listens to it, whether by design or by accident. The whisper is always there, older than galaxies, older than stars, older than the earth. A signal so patient that it has waited billions of years for minds capable of hearing it. And when those minds finally listened, they discovered not just a sound, but the story of everything. When the discovery of the cosmic microwave background was first announced, it sounded like a contradiction wrapped in silence. It was not a light seen by the eye, but a faint murmur in the spectrum of microwaves. A glow spread evenly across the entire sky. Everywhere the great radio horns and dishes turned, they were met with the same unyielding background. A signal that did not belong to any one star or galaxy or cluster, but to the universe itself. It was as if creation had poured a uniform paint across the heavens, smooth to a degree that defied expectation. For centuries, the night sky had appeared irregular, filled with constellations, voids, and the scattered fire of distant suns. Chaos seemed natural, structure inevitable. So how could the first visible memory of the cosmos be so impossibly even, with every direction showing the same temperature, the same pale whisper, to a precision of 1 part in 100,000? The shock was not simply that a background glow existed, but that it existed everywhere, identical and unavoidable, an ocean of sameness where one expected turbulence and difference. This revelation struck at the heart of one of the most profound questions in science. Had the universe always been, or had it begun? Until that moment, cosmology was divided into 2 visions of time. One was the Big Bang, the idea that all space and time emerged from a hot, dense beginning, expanding outward and cooling as it aged. The other was the steady-state model, a cosmos eternal and unchanging on the largest scales, continuously creating matter to maintain its balance as it expanded. The cosmic microwave background tilted the scales with elegance and force. If the universe were eternal and steady, no glow of fire should remain. No echo should bathe every corner of the sky. Yet here it was, a fossil of heat stretched thin across time, a message only the Big Bang could have written. The paradigm cracked. The steady state, once embraced for its philosophical comfort, an eternal cosmos, immune to birth or death, could not withstand the evidence the universe had not always been. It had been born, and the whisper of its infancy was now caught in radio horns and cryogenic detectors, in satellites and space observatories, in the quiet insistence of numbers. Yet even as the discovery confirmed the birth of time, it raised questions that seemed paradoxical. Why was the glow so smooth? In a universe only hundreds of thousands of years old, one would expect violent irregularities, regions hot with dense matter, regions cool and empty, a patchwork of chaos frozen into the afterglow. Instead, the cosmic microwave background was uniform to a fault, a balance of temperature so precise it suggested a strange conspiracy of physics. How had parts of the cosmos, separated by vast distances and with no opportunity to communicate, arrived at the same state, the same degree of equilibrium? This puzzle would come to be known as the horizon problem. Regions of the universe that appeared identical in temperature had never had time to exchange energy or information. Light had not traveled far enough in the short infancy of the cosmos to carry heat from one region to another. And yet, across the sky, the temperatures matched. The smoothness mocked the very rules of causality. It suggested that the cosmos was not only born, but born in a way that defied the simple unfolding of time and space, as then understood. The implications grew deeper. If the cosmos began hot and dense, and then cooled as it expanded, what force had guided this balance so delicately? Why was the universe neither collapsing back into itself, nor dispersing into a chaos of uneven temperatures? The smooth glow implied a fine-tuning that demanded explanation, a whisper that seemed to hint at laws not yet written into physics. Einstein had glimpsed such strangeness decades earlier, though he had resisted its consequences. In 1917, when he applied his general theory of relativity to the cosmos, his equations suggested that the universe should not remain static. Gravity, unchecked, would pull matter together, forcing collapse. To counter this, Einstein inserted what he called the cosmological constant, a mathematical device to hold the universe steady. To keep it eternal, he distrusted the vision of a universe in motion. A static cosmos felt safer, less disruptive to philosophy. But in 1929, Edwin Hubble peered through his telescope at galaxies beyond the Milky Way and discovered that they were retreating, their light stretched toward the red, fleeing in all directions. The universe was expanding, just as Einstein's original equations had suggested. Reluctantly, Einstein abandoned his constant, calling it his greatest blunder. Yet the consequences of his equations were now unavoidable. The universe had once been smaller, denser, hotter. If traced backward, expansion led inevitably to a beginning. The discovery of the cosmic microwave background sealed that fate. It was not simply an inference of equations, nor the distant redshift of galaxies, but a direct relic of the early universe itself. The glow should not exist in a steady cosmos. It should not exist in a universe without beginning. And yet it did, spread across the heavens like an eternal confirmation. But even as cosmologists celebrated the triumph of the Big Bang, the glow unsettled them with its unnatural perfection. It forced the question, what hidden process in those earliest instants had smoothed the universe so completely, ironing out the chaos into such uniformity? The uniformity was not a comfort, but a riddle, an invitation to rethink the first moments of creation. Philosophically, the whisper carried a weight beyond numbers. It revealed that the universe was not eternal, not a stage without origin. It had a first breath, and that breath had left its trace. Yet it also revealed that the first breath was strangely ordered, that the universe had been born not in turbulence, but in eerie equilibrium. It was like finding an infant with the calm face of an ancient sage, a newborn already bearing the quiet wisdom of balance. To scientists, this balance hinted at unseen mechanisms, forces that operated in the first fraction of a second, smoothing and aligning the cosmos in ways that ordinary physics could not explain. It whispered that the birth of time was accompanied by processes yet undiscovered, by laws hidden deep in the fabric of space-time. The cosmic microwave background was not only evidence of the Big Bang, it was evidence that the Big Bang itself had mysteries woven into its heart, and so what began as a hiss of static became a revolution. A glow that should not exist became proof of origins. A smoothness that defied expectation became the foundation of new theories. The cosmos had spoken in a whisper, and the whisper was stranger, deeper, more haunting than anyone had imagined. The glow is still with us. It falls invisibly across the Earth each moment, photons stretched into microwaves, reminders of the universe's first light. It is equal in all directions, as if to say that no place is more central than another, that the birth of time belongs to every horizon equally. But behind its calm uniformity lies the paradox. It should not be so smooth, it should not be so perfect, and in that imperfection of expectation lies the next great mystery, waiting to be unraveled. For decades after the discovery of the cosmic microwave background, the whisper remained a monotone hum. It proved the universe had a beginning, but it appeared almost too perfect, too uniform, a featureless veil spread across the sky. If this afterglow was truly the seedbed of everything, of stars, galaxies, and worlds, then somewhere within it, there had to be pattern, there had to be ripples, tiny variations written into the first light, like the grain of wood that foretells its future shape. But from Earth, the atmosphere blurred and drowned those delicate signals. The whisper was audible, but its finer notes were hidden. The answer came in 1989, when NASA launched a satellite named COBE, the Cosmic Background Explorer. It was humanity's first attempt to carry instruments above the distortion of the atmosphere, into the clarity of space, to listen directly to the oldest light in the universe. COBE's detectors were designed with extraordinary precision, cooled to temperatures near absolute zero, so that they themselves would not glow and drown the signal they sought to measure. For years, it orbited the Earth, mapping the sky in microwaves, pixel by pixel, until a picture began to form at first. The map seemed blank, the uniform glow still mocking the search for irregularity. But when the data was refined, when the subtle differences were teased out, the truth revealed itself. Across the sky lay ripples, faint fluctuations in temperature no larger than 1 part in 100,000. These were the fingerprints of creation, regions slightly warmer, regions slightly cooler, the earliest, imprints of density differences that would, under gravity's hand, grow into galaxies and clusters of galaxies. George Smoot, one of the lead scientists on COBE, described it as looking upon the face of God. What he and his colleagues saw was nothing less than the universe as an infant, a baby photograph of everything. It was the blueprint of cosmic structure frozen into the fabric of space, the moment when potential first began to divide into form. The revelation was staggering. These slight variations, mere whispers within a whisper, were precisely what cosmologists had long hoped to find. They were the seeds of all that would follow. Without them, the universe would have remained a uniform fog, a smooth soup of matter without structure, without galaxies, without stars, without life. In the unevenness of the cosmic microwave background lay the possibility of everything. COBE's map was crude by later standards, but it was proof, a confirmation that the whisper was not featureless after all. The afterglow carried memory, and within that memory lay structure. The universe was not born only with uniformity, but with the faintest of imperfections, and those imperfections were destiny. A decade later, the search turned sharper. In 2001, NASA launched a new satellite, the Wilkinson Microwave Anisotropy Probe, WMAP. Its mission was to refine what COBE had begun, to map the variations in exquisite detail, to resolve the face of the infant cosmos with clarity never before imagined. For 9 years, WMAP scanned the heavens, producing maps of the microwave sky with hundreds of times the resolution of COBE. The results revealed a tapestry of ripples, a mottled pattern of hot spots and cold spots stretched across the sky like a cosmic fingerprint. Each patch of light represented a density contrast in the early universe. Slightly denser regions where matter pooled, slightly thinner regions where it drained away over billions of years. These ripples would magnify under gravity's relentless pull, collapsing into filaments, clusters, and superclusters, the vast web of galaxies that fills the universe today. From the patterns, cosmologists could read the composition of the universe with uncanny precision. They saw that ordinary matter, the atoms that build stars and planets, made up less than 5% of the total. The rest was divided between dark matter, the invisible scaffolding upon which galaxies form, and dark energy, the mysterious force driving cosmic acceleration. All of this, the invisible, the unfathomable, was encoded in the baby photograph of the universe, written into the first light. MAP did more than reveal structure. It measured the age of the cosmos with stunning accuracy, 13.7 billion years. It confirmed the geometry of the universe as flat on large scales, stretched across space-time like a vast Euclidean sheet. It was as though the whisper itself had spoken its age, its shape, its hidden contents, in a language of temperature and fluctuation. And still, the story deepened. In 2009, the European Space Agency launched the Planck satellite, the most sensitive probe of the cosmic microwave background ever built. Its detectors were cooled to just 1/10 of a degree above absolute zero. Its resolution was finer than anything before, capable of mapping the sky with detail down to arc minutes, sensitive to variations so slight they seemed almost beyond possibility. For 4 years, Planck listened to the whisper with unmatched precision, and when its data was released, the universe revealed itself in unprecedented clarity. The Planck map was breathtaking, a glowing oval filled with ripples, a portrait of the universe when it was only 380,000 years old. Every filament of structure that would one day emerge was present in embryonic form. The baby photograph was now crystal clear, and from it cosmologists could read the history of cosmic evolution like scripture. Planck confirmed the strange dominance of dark matter and dark energy. It refined the age of the universe to 13.8 billion years. It revealed subtle anomalies, alignments, and cold spots that defied easy explanation. And above all, it proved that the first light of the cosmos was not mute, but filled with information, a library of the earliest moments of time. To look upon these maps is to stand at the threshold of origin. Every cold patch, every warm ripple, is a seed of what became galaxies, stars, worlds, and life. The Milky Way itself was born from one such ripple, a faint unevenness in the ancient fireball. In this sense, each map is not only a picture of the universe as a whole, but also a portrait of ancestral memory. The faint imperfections in the whisper shaped everything that followed. The ripples are our lineage, written in light. The emotional weight of these discoveries is profound. For the first time, humanity could look not at stars or galaxies as they are now, but at the raw beginnings from which they grew. It is the closest science has come to capturing the moment when potential became reality, when a universe of possibility crystallized into the patterns that would one day give rise to life. The baby photograph is not silent. It speaks of destiny, of structure, of inevitability. It whispers that from chaos comes form, from imperfection comes creation. Yet within the triumph lies mystery. The maps are not entirely smooth, nor entirely random. Some features defy simple explanation. A vast, cold spot in one region, curious alignments across the sky. These anomalies remain puzzles, hints that the story of the first light is not yet complete. Even in its clarity, the whisper retains its secrets. But what is undeniable is this. With Kobe, Hubble map, and Planck, humanity has learned to see the universe as an infant. The maps are portraits of the cosmos at its most fragile, its most pure, its most revealing. They are the earliest photographs ever taken, snapshots not by cameras, but by physics itself, preserved in photons that have traveled unbroken for nearly 14 billion years. To gaze upon them is to gaze upon time itself, caught in a single image. The cosmic microwave background is more than a relic. It is a testament. It proves that the universe remembers its birth and that memory can be mapped, measured, and read. And in those maps lies not only the story of galaxies and stars, but the story of humanity's place within them. We are the descendants of ripples. We are the children of imperfections frozen into light. And in the faint glow of the oldest photograph, we find both our beginning and our future. The maps of the oldest light seemed at first like triumphs of order, from Kobe to W map, and finally Planck. The baby photograph of the cosmos revealed a pattern of ripples and spots, just as theory had predicted. The universe had been born with structure, small imperfections that grew into everything. It appeared to confirm the elegance of the Big Bang, the consistency of cosmic evolution, and yet, hidden within the perfection were blemishes, subtle distortions, quiet irregularities that resisted explanation. When the cosmic microwave background was scrutinized with the finest instruments humanity had ever built, it did not reveal only harmony. It revealed anomalies. The most striking of these lay in the southern hemisphere of the sky, a region known simply as the cold spot. Unlike the ordinary fluctuations seen elsewhere, this patch stretched far wider, a vast ellipse of space inexplicably colder than its surroundings. Its temperature difference was slight, a few tens of millionths of a degree, but its scale was immense, spanning hundreds of millions of light years. In projection, too large, too pronounced to be easily dismissed. The cold spot defied the expectations of randomness. In the standard cosmological model, the ripples of the microwave background should appear like static, random, uncorrelated, with no favored directions or shapes. Yet here was a patch so distinct, so persistent, that its very existence seemed to whisper of something hidden. Some suggested it could be the shadow of a cosmic void, an immense region of the universe where matter is unusually sparse. As photons from the early universe crossed such an emptiness, they would lose energy in a subtle effect known as the integrated Sachs-Wolf effect, cooling slightly as they journeyed through expanding space. But even the largest voids known could not account for the scale and depth of the cold spot. It remained too strong, too anomalous, too resistant to ordinary explanation, and the cold spot was not alone. As data from WMAP and later Planck was analyzed with mathematical rigor, another strangeness emerged. The tiny fluctuations across the microwave sky, which should have been distributed without preference, seemed to exhibit alignments. Across vast distances, hot and cold patches appeared oriented along a particular axis. This mysterious alignment was dubbed the axis of evil, a phrase borrowed from politics but now immortalized in cosmology. The name was tongue-in-cheek, but the puzzle was real. If the fluctuations were truly primordial, imprinted at the birth of the universe, then no direction should be special. The cosmos, on the largest scales, should be isotropic, the same in every direction. Yet the axis of evil suggested otherwise. Temperature patterns appeared to line up with the plane of our solar system, as though the whisper of the Big Bang were somehow aware of Earth's place in the cosmos. For cosmologists, this was unsettling. It raised the possibility that the maps were contaminated, perhaps by foreground emissions from dust in the Milky Way or subtle systematic errors in measurement. But even after years of correction, calibration, and refinement, the alignments persisted. What should have been pure randomness still seemed to carry structure. The implications were disquieting, if real. The anomalies hinted at physics beyond the standard model of cosmology. Some speculated they could be imprints of other universes, collisions between cosmic bubbles in a grander multiverse, leaving scars in the microwave sky. Others wondered if they pointed to new physics of inflation, the rapid expansion thought to have set the initial conditions of the cosmos. Or perhaps they were signs of something even stranger, features of space-time itself we do not yet comprehend. The axis of evil became a source of both fascination and caution. Some argued that the anomalies might be nothing more than statistical flukes, the chance patterns that emerge when randomness is stretched across a vast canvas. After all, in any large data set, unexpected coincidences appear, but the persistence of these features, across different instruments and missions, refused to fade into noise. The cold spot, too, resisted dismissal. If it was not a void, if it was not mere coincidence, then it demanded something deeper. One radical interpretation suggested it might be a signature of a multiverse, the aftershock of another universe brushing against our own in the first instance of creation. Such collisions could, in theory, leave imprints in the microwave background, vast distortions that no ordinary cosmology could explain. If true, the cold spot would be the first evidence that our universe is not alone, yet science moves carefully, bound by rigor. Extraordinary claims require extraordinary proof. And so, for now, the anomalies are treated with restraint, filed under puzzles awaiting resolution. They are neither dismissed entirely nor embraced without caution. They hover at the edge of understanding, whispers that may one day become revelations. Still, there is something deeply human in their allure. The cosmic microwave background was supposed to be simple, an elegant confirmation of theory. And yet, within its perfection, lie imperfections, smudges, alignments, peculiarities. It is as if the universe itself resists complete comprehension, offering truths with one hand while concealing others with the other. The axis of evil remains a riddle. The cold spot remains a wound in the fabric of the microwave sky. Together they remind us that even in the most ancient light, certainty is elusive. The cosmos offers maps, but not always explanations. Perhaps they are flukes, perhaps they are errors, or perhaps they are the first hints of a deeper order, one in which our universe is but a fragment of a greater whole. For now, the anomalies stand as quiet provocations. They remind cosmologists that the story of the beginning is not finished, that the whisper of the Big Bang carries not only clarity, but also mystery. The oldest light does not merely confirm what we expect. It teases, it unsettles, it defies. And in doing so, it keeps the human search alive. The cold spot and the axis of evil remain as scars upon the baby photograph of the universe. They are blemishes that refuse to vanish, reminders that the cosmos is both knowable and unknowable, a puzzle that yields just enough to keep us listening. In their presence, one truth becomes clear. The universe, even at its most revealing, keeps secrets still. The first maps of the cosmic microwave background revealed a universe young and fragile, just 380,000 years after its birth. A universe painted with astonishing uniformity. Everywhere the telescope turned, it saw nearly the same temperature, the same soft afterglow, differing only in faint ripples a few parts in 100,000. It was a vision of perfection, and yet, within that perfection lay a paradox. This light had traveled for more than 13 billion years, reaching Earth from regions of space separated by immense gulfs. And still, they appeared identical, as though coordinated, as though they had shared the same history. But according to the speed of light, they could never have touched. No signal, no warmth, no whisper of information could have crossed those gulfs of distance in the brief infancy of the cosmos. And so arose one of the greatest riddles in modern cosmology. The horizon problem. Imagine two far-flung regions of the sky, separated by billions of light years today. Both show the same microwave glow, the same cosmic temperature. Yet, in the first 380,000 years, there was not enough time for any exchange to equalize them. How then did the universe achieve this eerie uniformity? How did such distant regions conspire to match, as if tuned to the same cosmic note? The cosmic microwave background did not solve this problem. It deepened it, for its smoothness was too perfect, too precise. Without explanation, it seemed almost unnatural. A universe that should have been patchy, chaotic, uneven, instead appeared finely balanced, as though crafted with impossible care. And beyond the horizon lay another puzzle, the flatness problem. The microwave maps revealed that the geometry of the cosmos is astonishingly close to flat. In the language of Einstein, space-time can bend under the weight of energy and matter, curving like a sheet stretched by unseen hands. A closed universe, heavy with matter, would curve back upon itself, collapsing into a final fire. An open universe too light would expand, forever, thinning into an eternal frost. But the data showed something different. A balance so exact, it defied comprehension. The density of matter and energy in the early cosmos was tuned within a fraction of 1% to yield a universe that appeared flat on cosmic scales. This precision was staggering. If the universe had been only slightly denser at its birth, it would have collapsed within millions of years. If only slightly thinner, it would have raced outward too quickly for stars and galaxies to form. Yet it was neither. It balanced upon a knife edge between fire and emptiness, perfectly poised, sustaining billions of years of evolution. The microwave background made this balance visible. Its ripples confirmed that the early cosmos was delicately tuned. But it offered no reason why the question lingered, sharp and unsettling. Why should the universe be born so exact, so improbably balanced? And then came the third riddle, the mystery of initial conditions. Why was the universe so ordered at all? Entropy, the measure of disorder, is expected to rise with time. If so, the beginning should have been the most chaotic of all, the rawest storm of randomness. Instead, the cosmos began with breathtaking order, low entropy, smooth horizons, and finely tuned density. It was not chaos, but elegance, not confusion, but clarity. The microwave background preserved this memory, a baby photograph that showed a cosmos already poised for harmony. For physicists, these puzzles struck at the very heart of understanding. The horizon problem whispered of impossible communication across the infant universe. The flatness problem spoke of balance without explanation. The problem of initial conditions demanded to know why the universe began in a state so precise, so special, that life and galaxies could one day emerge. Einstein's equations had hinted at expansion, at dynamism in the fabric of space-time, but they did not explain such perfection. For decades, cosmologists wrestled with these questions, searching for a framework that could account for the whispering light. Some turned to philosophy, wondering whether these conditions were simply given, brute facts beyond explanation. Others sought deeper physics, hidden mechanisms that might impose order upon chaos. The cosmic microwave background was not silent in this debate. Its smoothness was the evidence, its perfection, the riddle. Every ripple measured by Kobe, W-map, and Planck only sharpened the paradox. The more precise the data, the stranger the beginning appeared. It was as though the cosmos itself was both generous and mocking. Generous in revealing its earliest portrait, mocking in how that portrait refused to align with expectation. A universe that should not have been so smooth was smooth. A universe that should not have been so flat was flat. A universe that should have been chaotic was astonishingly ordered. This tension deepened the mystery of existence, for if the cosmos were born chaotic, it would not hold galaxies, stars, or life. But if it were born perfectly ordered, one must ask, why? What principle, what hidden process sculpted the universe into such uncanny balance? The microwave background offered no answers. It only posed the questions more sharply. It was a whisper of creation that seemed to say, the beginning was stranger than you imagine. Cosmologists began to sense that the standard picture was incomplete. The puzzles of horizon, flatness, and initial conditions could not be explained by simple expansion alone. Something more was needed. A new idea, a radical reimagining of the earliest moments when the laws of physics themselves may have behaved differently. And so, from the silence of the microwave sky, emerged the seeds of a revolutionary theory. One that would suggest the universe did not simply expand, but exploded outward with unimaginable speed, smoothing, flattening, and setting the stage for all to come. But that answer, the theory of cosmic inflation, was still to arrive in the glow of the microwave background. Humanity stood at the threshold of deeper mysteries, aware that the universe, in its perfection, was asking the hardest of questions. The smoothness of the universe was a riddle that would not fade. The horizon problem, the flatness problem, the mystery of initial conditions, each demanded an answer. Each pointed to a flaw in the simple picture of a universe expanding slowly. From a fiery beginning, the cosmic microwave background sharpened the questions. but offered no solution. The whisper of creation seemed to say, something is missing in the late 1970s and early 1980s. A young physicist named Alan Guth wrestled with these puzzles. Working late into the night, searching for a mechanism that could explain the universe's improbable balance, he stumbled upon an idea so radical it would alter cosmology forever. It was called inflation. The premise was simple, yet staggering. In the first fraction of a second after the Big Bang, far earlier than the release of the microwave background, the universe may have undergone a burst of expansion faster than anything imagined. Not merely expansion, but exponential growth. In less than a trillionth of a second, the cosmos could have ballooned from subatomic scales to something macroscopic, smoothing and flattening everything in the process. Such an event would have consequences profound enough to solve the riddles. Distant regions that appeared identical in the microwave background could once have been close, before inflation tore them apart. Their uniformity was not coincidence, but shared origin. The flatness of the universe was no longer puzzling. Inflation would have stretched space-time so enormously that any curvature would be ironed away, like wrinkles smoothed on an endless sheet. Even the improbable order of the initial conditions could be explained. Chaos existed, but inflation magnified a patch of space into a vast cosmos, carrying its uniformity outward into everything. The theory did more than answer. It offered predictions for inflation would not only stretch the universe, it would stretch the fabric of quantum reality itself, quantum mechanics. The science of the very small tells us that fluctuations are inevitable. Particles flicker in and out of existence. Energy trembles at every scale. Normally, these fluctuations vanish into insignificance, but during inflation, the expansion was so violent, so immense, that microscopic quantum tremors were dragged outward to cosmic proportions. Tiny fluctuations in density became the seeds of structure. The ripples seen in the cosmic microwave background were the fingerprints of quantum. Fluctuations stretched into the pattern that would one day grow into galaxies and clusters. Inflation turned the random noise of the quantum world into the blueprint of the universe. It linked the smallest scales of existence to the largest. It tied the flicker of subatomic particles to the distribution of stars across billions of light years. Cosmologists soon realized that the theory of inflation was not only elegant, but testable. If it truly occurred, it should leave signatures in the microwave background beyond simple temperature maps. It would leave traces in polarization, the subtle orientation of light waves. Most striking of all, it could produce a unique signal. B-modes are a twisting, curling pattern in the polarization of the microwave background. Unlike the smoother E-modes, which arise from density fluctuations, B-modes would be generated by gravitational waves, ripples in space-time itself, born in the violence of inflation. If detected, they would be the smoking gun, the direct imprint of inflation upon the oldest light for decades. The search for B-modes became one of the most ambitious quests in cosmology. Telescopes were placed on mountaintops and in Antarctica, instruments cooled to near absolute zero, detectors tuned to sift the faintest whispers from the static of the universe. The goal was simple: find the curling polarization that would confirm inflation as more than a dream. In March of 2014, excitement surged across the scientific world. A collaboration known as BICEP-2, stationed at the South Pole, announced that they had seen it. The swirling signature of B-modes seemed to appear in their data. The first glimpse of inflation's fingerprint, a triumph decades in the making. For a moment, it seemed the universe's deepest riddle had been cracked. The story of creation was no longer incomplete. The inflationary dream had taken its first breath of reality. But science demands caution. Other teams quickly began reanalyzing the data, comparing it with observations from the European Space Agency's Planck satellite. What they found was sobering. The signal BICEP-2 had detected could be explained not by primordial gravitational waves, but by dust in the Milky Way. Microscopic grains of carbon and silicate aligning with magnetic fields, scattering light in ways that mimicked the expected pattern. The triumph dimmed into controversy. Inflation was not disproven, but neither was it confirmed. The smoking gun remained elusive, hidden beneath cosmic dust and the limitations of technology. And yet, the dream persists. Inflation remains the leading explanation for the puzzles of the microwave background. Its predictions align with the observed smoothness, the flatness, the distribution of ripples across the sky. Even without B-mode confirmation, the theory elegantly accounts for the mysteries that otherwise defy reason. Cosmologists continue to search, new instruments are being built. The Simons Observatory in Chile, the CMB-S4 experiment across the globe, missions designed with unprecedented sensitivity. Each seeks the elusive signature of inflation, the curling imprint of space-time waves born in the first instant of time. The inflationary dream is not merely science. It is philosophy, a vision of beginnings. It suggests that the universe we see is but one bubble among many, that inflation may have spawned countless others, each with its own laws and constants. It implies that our cosmos is both unique and not unique, a single leaf upon a vast and unseen tree. And so the whisper of the microwave background continues to challenge. It carries not only the memory of a smooth, balanced beginning, it carries the promise of an answer hidden in polarization, in subtle patterns that no eye can see, only instruments can capture. Inflation remains a dream suspended between proof and speculation, a theory that answers the impossible with elegance, yet still awaits its decisive evidence in its vision. The smallest flickers of quantum energy sculpted the grandest architecture of the cosmos. In its promise lies the possibility that the universe itself is the echo of a moment so brief, so violent, and so transformative that it remade reality in less than the blink of an eye. The dream endures because the questions remain. The horizon problem still whispers. The flatness problem still lingers. The mystery of initial conditions still presses upon the imagination. Inflation offers a way through, a vision of how the impossible could have become real, and whether proven tomorrow or in centuries, it reshapes how humanity gazes upon the sky. For it reminds us that the universe was not merely born, it may have inflated, erupted, blossomed from quantum whispers into the vast cathedral of space and time. The inflationary dream is the story of how the cosmos may have become smooth, but it is also the story of how human thought stretches, like the universe itself, to seek the unseen, to test the impossible, and to listen ever more carefully to the oldest whisper of light. The cosmic microwave background may appear to the untrained eye as nothing more than a faint, static glow spread evenly across the heavens. But within that glow lies a ghostly archive of forces that have never been seen directly. Invisible sculptors that shaped the very geometry of the cosmos by the early 2000s. Cosmologists had already begun to suspect that most of the universe was missing from view. Not missing in the sense of absence, but missing in the sense of invisibility. A presence felt only through its gravitational pull, its quiet hand tugging on the fabric of galaxies' dark matter, the unseen scaffolding on which every star and galaxy is strung, and darker still, dark energy, a repulsive pressure pushing space itself apart, accelerating the universe's expansion into a cold future. And though neither can be touched or seen with telescopes of glass or mirrors of silver, the CMB provides their fingerprints. For in the most delicate ripples of that ancient light, the invisible makes itself known. When a photon of the cosmic microwave background began its journey, nearly 13.8 billion years ago, it carried a story. It threaded through an infant universe still thick with matter and gravity. And as it traveled forward, those faint particles of light were bent and deflected by invisible concentrations of mass, halos of dark matter that no eye could ever see. This bending, this subtle distortion, is called gravitational lensing. It is the universe itself acting as a vast and patient magnifying glass by tracing the slight twists in the polarization of CMB light. Missions like Planck revealed the unseen skeleton of the cosmos maps of the dark matter web, a lattice stretching between galaxies, unseen but essential, began to emerge. The galaxies, bright and visible, appeared merely as lanterns hanging on the bones of an invisible beast. Without this unseen mass, galaxies could not cling together. Stars would drift apart like fireflies in an endless night. The cosmos, as it is known, could not exist. But the shadows deepen further still. For beyond dark matter lies a greater enigma. Dark energy, a force not binding but repelling. While dark matter pulls galaxies inward, dark energy pushes them apart. The evidence comes from another subtle signature in the CMB, the integrated Sachs-Wolf effect. As CMB photons journey across billions of years, they traverse valleys and peaks in the cosmic gravitational landscape. If the universe contained only matter, the deep wells of gravity carved by clusters of galaxies would remain steady. But because the expansion of the universe is accelerating, these wells slowly decay. A photon falling into such a well and then climbing back out does not lose exactly what it gained. It emerges slightly warmer, slightly shifted, a whisper of dark energy carved into its spectrum. By measuring these tiny distortions, scientists glimpse the hand of dark energy, a faint ripple superimposed on the oldest light. It was a revelation almost too immense to bear, that the majority of the cosmos was not only invisible, but actively shaping the universe's destiny. The implications are staggering. Roughly 5% of the universe is made of familiar matter. Atoms, stars, planets, every mountain and sea. About 27% is dark matter, invisible, yet gravitationally indispensable, and nearly 68% is dark energy, a pressure that seems to dwell within the vacuum of space itself. Together, they form a haunting ratio. 95% of the cosmos cannot be seen, cannot be touched, cannot be held. The CMB became the first great ledger of this imbalance, a reminder that human senses are tuned only to the smallest fraction of reality, that the cosmos, in its true essence, hides behind veils of darkness. And yet, even as darkness defines most of the universe, the CMB offers a strange kind of comfort, because its photons, those fragile travelers, interact with everything, both visible and invisible. They remember where dark matter bent them. They recall where dark energy lifted or weakened the wells they passed through. They return to detectors on Earth carrying stories that no eye could have perceived otherwise. The CMB is not only a photograph of the infant universe, it is also a mirror reflecting the hidden forces that still shape the universe today. Its ripples are whispers of the unseen, echoes of battles between gravity and expansion. It reveals that the greatest actors in the cosmic drama are not the stars, but the shadows that cradle and repel them. And so cosmology enters a paradoxical age. An age in which the universe is mapped, in exquisite detail, and yet most of its substance remains unknown. An age in which the shadows are more real than the light, and the invisible outweighs the visible. The CMB stands at the center of this paradox, a relic of fire, carrying within its delicate pattern the blueprints of forces that human beings can only name, but not yet understand. Dark matter, dark energy. Concepts as vast and elusive as the cosmos itself. They do not shimmer in the telescope's glass. They do not glow in the astronomer's lens, and yet their weight is undeniable, their pressure unavoidable. The oldest light of the universe has revealed their existence, but it has not yet told their story. That story remains in the shadows, waiting for another generation of instruments, another century of thought, another spark of human imagination. For now, the CMB holds its silence. It whispers only enough to remind humanity of how little is known, that the cosmos is not made only of stars, but of mysteries far greater that the truest map of the universe is not drawn in light but in shadow. From the faint afterglow of the Big Bang, the cosmic microwave background does more than whisper about the infant universe. It also offers a ruler, a scale, a way of measuring the very breadth of the cosmos. Encoded within its ripples is the story of how fast space itself expands, a number that cosmologists call the Hubble constant for decades. This number was thought to be the key to time itself. If the universe is expanding, then knowing the rate of that expansion unlocks its age, its history, and its destiny. The CMB, frozen when the universe was only 380,000 years old, carries within its patterns a pristine record of those earliest motions. By analyzing its ripples, missions like Planck derived a value for the expansion rate, about 67 kilometers per second per megaparsec. A number precise, elegant, and self-consistent within the framework of the standard model of cosmology. But the universe has never been so obedient as to let itself be pinned down with certainty. Astronomers, unwilling to rely only on ancient light, sought confirmation in the nearer cosmos. They turned their gaze to pulsating stars, Cepheid variables, whose rhythmic brightening and dimming allowed their distances to be measured with remarkable accuracy. They traced the light of Type Ia supernovae, exploding, stars that shine with a nearly uniform brilliance, serving as cosmic mile markers scattered across billions of light years. From these local measurements came a different number, not 67 but 73, a faster rate of expansion, a universe younger than the one implied by the CMB. The disagreement was small in appearance but enormous in consequence. Two ways of measuring the same cosmic truth had produced incompatible answers. This fracture in cosmology became known as the Hubble Tension, not merely a technical dispute but a philosophical wound. For if the universe tells two stories about its own expansion, which is to be believed? Was the early universe encoded in the CMB subtly different from the universe that unfolds before telescopes today? Was there something missing in the great equations, a hidden chapter in cosmic history not yet imagined? The tension is not a trivial error. The uncertainties have been scrutinized, calibrated, recalibrated, and yet the gap remains. Statistically, the divide is now large enough to suggest more than coincidence, a signal, perhaps, of new physics hiding in plain sight. One possibility is that dark energy itself is not constant, that the mysterious pressure accelerating the universe today has not always been the same. If it evolved over cosmic time, then the early universe measured by the CMB would not perfectly align with the universe observed through supernovae and Cepheids. In this vision, the cosmos is not governed by a single immutable constant, but by a restless force shifting across epochs. Another possibility lies deeper still, in the notion of early dark energy. Perhaps a fleeting burst of repulsive energy filled the universe, in its first few 100,000 years, altering the sound waves imprinted in the CMB. Such a hidden ingredient would ripple forward into the present, changing the scale on which expansion is measured. It would be a revision to the very recipe of the cosmos, a new chapter added to the standard model. Still others wonder whether unseen particles, sterile neutrinos, or forms of matter yet unnamed, could resolve the divide. For every attempt at reconciliation stretches the imagination into territory not yet confirmed, but not yet ruled out. Some insist that the tension reflects only human error, that the measurements of Cepheids and supernovae, delicate as they are, remain vulnerable to subtle biases, that the calibration of cosmic distances, the cosmic distance ladder, might yet conceal systematic mistakes. If so, the conflict may be no more than a mirage of imperfect instruments, destined to fade as precision sharpens, but if not, then cosmology stands at the threshold of a deeper revelation. A sign that the standard model, so successful in explaining the broad sweep of cosmic history, is incomplete. A hint that something fundamental waits beyond the horizon of current understanding. The philosophical weight of this disagreement cannot be overstated. Science rests on the premise that the universe is coherent, that it's different. Measurements must ultimately converge on a single truth. But here, the cosmos seems to speak in two voices, one whispering from the infant universe, another from the stars of today, both clear, both precise, and yet both irreconcilable. It is as though the universe is both younger and older than itself, as though its story bends in two directions at once, a contradiction not easily set aside. This fracture has left cosmologists in a state of unease, for if the CMB cannot be fully trusted, then the great map of the early universe may be subtly distorted. And if the local measurements are the ones in error, then every distance and every estimate built upon them may require re-examination. In either case, a cornerstone of modern cosmology quivers under the strain to those who seek certainty. This tension feels like a betrayal, a reminder that the cosmos is not obliged to confirm human expectation. To those who seek discovery, it feels like a gift, for in the fracture between two truths lies the possibility of new horizons. The Hubble tension is not simply a puzzle of numbers, it is a philosophical riddle about the nature of knowledge itself, about whether the universe can ever be captured in a single story, or whether it is destined always to speak in echoes, leaving humanity to trace the outlines of a truth too vast for comprehension. And so the debate continues. New telescopes rise on mountain peaks and in orbit, each designed to measure the expansion rate with sharper clarity. The James Webb Space Telescope refines the distances to Cepheids and supernovae. Surveys of galaxies trace the large-scale structure with unprecedented depth. Gravitational waves, rippling from colliding neutron stars, promise an independent measure of the expansion rate, a standard siren to test against both ancient and local methods. Each new approach tightens the net, but the gap refuses to close. The numbers remain stubbornly apart. The universe continues to tell two stories. Perhaps the cosmos is not lying. Perhaps it is revealing. Perhaps the tension is not a flaw in measurement, but a window into something greater than the current imagination allows. The story of the Hubble constant has become the story of humility, a reminder that even in an age of exquisite precision, the universe holds back its deepest secrets, that the CMB, glowing faintly in microwaves across the sky, may be as much a veil as it is a revelation, that every answer uncovers not certainty, but a deeper question. In this way, the Hubble tension is not a wound to cosmology, but its pulse. It is the mark of a science alive, reaching beyond its limits, unsettled by its own discoveries. A sign that the cosmos, vast and ancient, will not yield its truth without struggle. The expanding disagreement remains a tension between early and late, between light that has traveled 13 billion years and stars that flicker only a few million away, between the beginning and the present, between two truths that should be one, and in that fracture lies the future of cosmology. For whether it ends in error or in revelation, the universe has made one thing clear. Its story is not finished, its mystery is still deepening, and the final measure of its expansion remains written not in certainty, but in shadow. The cosmic microwave background is often described as the oldest light in existence, a relic from when the universe was only 380,000 years old. Yet even this light does not take us to the very beginning. It is a curtain that both reveals and conceals a final scattering of photons that marks the moment the universe first became transparent. Beyond that moment, before the fog of plasma cleared, light cannot reach. No telescope will ever pierce those depths, but the cosmos may yet be heard in other ways. For not all messengers are bound by the same rules as photons. Gravitational waves, ripples in the fabric of space-time itself, are older still. If the Big Bang was accompanied by violent bursts of energy, those waves would have surged outward, indifferent to the opaque plasma that once trapped light. they would still cross the universe today, faint beyond imagination, yet untouched, carrying with them the memory of moments far earlier than the release of the CMB. Such primordial gravitational waves remain undetected, but their possibility lingers as one of the deepest scientific hopes. If they exist, they could tell of inflation itself, the brief, dizzying expansion that may have sculpted the cosmos into its present smoothness. They could carry whispers from the very first instant, when known physics dissolves into speculation, and the line between creation and existence blurs. Neutrinos, too, offer another kind of echo. These ghostly particles, almost without mass, interact so weakly with matter that they passed freely through the dense early plasma long before light was released. The universe is bathed in a cosmic neutrino background, a sea of ancient particles still flowing silently across all of space. Their signature is faint, hidden within the delicate power spectrum of the CMB, subtly altering its ripples. Though not directly seen, their fingerprints affirm that even in the first seconds, when matter and antimatter annihilated, something survived to carry the memory forward together. These invisible messengers hint that the early universe is not entirely beyond reach, that if humanity learns how to listen beyond light, a truer beginning might yet be heard. Already, the CMB has begun to yield to such deeper listening subtle distortions. In its polarization, reveal the story of reionization, when the first stars and galaxies ignited hundreds of millions of years after the Big Bang. In their brilliance, they bathed the cosmos in ultraviolet light, stripping electrons from atoms and altering the CMB's delicate polarization pattern. It is faint, but it is there, a signature of the dawn of structure, inscribed on a canvas billions of years older than the stars themselves. The same technique, extended further, might reveal the faint curling patterns known as B-modes, polarization swirls, thought to be seeded by primordial gravitational waves. To detect them would be to hear the heartbeat of inflation itself, a discovery that would lift the veil beyond the CMB and into the first instant of time. The pursuit of such whispers drives a new generation of missions. Japan's Lightbird satellite, scheduled for launch in the coming decade, aims to map the polarization of the microwave background with exquisite sensitivity on Earth. The CMB S4 experiment, an array of thousands of detectors spread across Antarctica and Chile, will listen for distortions on scales finer than ever before. Together, they reach not for brightness, but for subtlety, for the faintest curls, the softest deviations, the smallest tremors in a nearly uniform sky. The goal is not merely to refine the map, but to break through it, to find in its fabric something that does not belong, a hidden law, an unimagined particle, or the faint echo of a time before time itself. For the dream of cosmology is not only to describe the universe as it is, but to understand the conditions that brought it into being. The CMB marks a boundary, a horizon of light. Beyond it lies a realm that photons cannot reach, but other messengers may. To read those signals is to glimpse a deeper layer of reality, perhaps even a pre-Big Bang era, if such a concept has meaning. Speculative theories imagine a cosmos born from the collision of higher dimensional brains, or the rebound of a previous universe collapsing into itself. If such events occurred, they might leave subtle scars, distortions in the CMB, patterns in primordial gravitational waves, or statistical imbalances beyond chance. To search for these is to ask whether the Big Bang was a beginning or merely a transition, whether the universe had a cause, or whether it has always been in some form of cycle beyond human comprehension. Even without stepping beyond, the act of listening deeper reshapes the understanding of what has already been seen. Each distortion, each ripple, each subtle alignment tells not only of physics, but of philosophy, that the universe is not silent, that every particle, every wave, every photon and neutrino carries memory within it, and that memory is not chaos, but story, a narrative written across billions of years, waiting only for the instruments that can hear its faintest tones the challenge is immense. The signals are faint enough to be drowned in the static of galaxies, the glow of dust within the Milky Way, the noise of the instruments themselves. Separating the cosmos from contamination requires not only technology, but patience, ingenuity, and humility. For what is sought lies at the edge of detectability, a whisper within a whisper, and yet progress continues. Each decade brings a sharper ear, a finer filter, a deeper sense of what is hidden within the ancient glow. What was once only noise now reveals patterns. What was once invisible now begins to cast a shadow. To listen beyond the light is to embrace uncertainty. It is to accept that the universe may hold truths that are fragile, easily obscured, always at risk of being lost in the vastness. But it is also to believe that nature does not conceal without reason, that the cosmos, however veiled, still longs to be understood. The pursuit is less about certainty than about possibility, for even if the ultimate origins remain forever beyond reach, the act of listening reshapes humanity itself. It expands the horizon of what can be asked, and in asking, redefines what it means to know, and so the search continues. For gravitational waves still echoing from the first instant, for neutrinos older than light itself, for the polarization swirls that may confirm inflation, for distortions that may reveal laws not yet written. The ancient whisper of the CMB was not the final word of the universe, but only the first that humanity could hear. Beyond it lie voices still fainter, still stranger, still waiting. The cosmos is not silent, but layered in harmonies. To hear them all is to approach the edge of the unknowable. Listening beyond the light is more than a scientific ambition. It is a philosophical calling. For in each faint echo lies a reminder that existence itself carries memory. That the universe is not merely matter and energy, but story. A story that began before the first photons were free. A story that may reach back into realms beyond imagination. And though its ending remains hidden, its unfolding continues. To be heard in light, in waves, in particles, in silence. The cosmos still whispers, and humanity is only beginning to learn how to listen. The cosmic microwave background is not only a relic of physics, it is a relic of meaning. For it reminds humanity that the universe itself is capable of memory. Every photon released in that ancient moment, nearly 14 billion years ago, has carried its history faithfully across the abyss of time. It has endured the birth of galaxies, the rise of stars, the formation of worlds, the long passage from chaos to order and from darkness to light. It has traveled without pause, without rest, arriving now as a faint whisper on the instruments of Earth. And in that whisper lies a truth so profound that it binds science to philosophy. The truth that existence itself remembers where it has been. To look into the CMB is not simply to see radiation from the past, it is to read the story of all that followed. For in those faint ripples are written the seeds of galaxies. In those minute variations are the first instructions for stars, for planets, for life itself. Every atom of the human body, every grain of soil beneath human feet, once moved to the rhythm encoded in that primordial glow. The CMB is therefore not distant. It is intimate. It is the oldest inheritance, the original script from which every living thing has been written. When humanity listens to its whisper, it listens also to its own origin. It is the cosmos telling its children the first chapter of their story. And yet, like all stories, it carries paradox. For the more it reveals, the more it conceals. It tells of smoothness, of strange uniformity, of hidden shadows called dark matter and dark energy. It hints at horizons beyond comprehension and at expansions that cannot be reconciled. It resolves some questions only by raising deeper ones. The whisper of the CMB is therefore both an answer and a riddle. It offers clarity while deepening mystery. It confirms that the Big Bang was real, that the universe has a beginning, but it also unsettles by asking what came before, what force set it in motion, what landscape it emerged from, and whether this universe is only one of many. The whisper is not a conclusion. It is an invitation. There is something profoundly human about this paradox. For human beings, too, are creatures of memory and mystery. They carry within their bodies the elements forged in ancient stars. They carry within their minds the questions that light alone cannot answer. The CMB becomes a mirror in which the cosmos and humanity recognize one another, both defined by what is known and by what cannot yet be known. To contemplate the CMB is to realize that knowledge is not a possession, but a horizon. The closer one moves to it, the more it recedes, drawing the mind ever onward into deeper wonder. The whisper also speaks of time itself. It proves that time is not an abstraction, but a fabric that can hold memory, that the present is never divorced from the past, but woven from it. And if the past can be carried forward in photons, perhaps the future too is already seeded within the present. Perhaps in the patterns of the CMB lie not only the story of what has been, but the outline of what will come. The expansion of the universe, the fate of galaxies, the ultimate cooling of all things into silence. The whisper does not tell these futures outright, but it suggests that the universe, in its deep memory, already knows how the story must unfold. For humanity, the CMB is a reminder of scale. The same photons that bathe the entire cosmos fall gently upon the instruments of a small planet orbiting an ordinary star. The same laws that shape the clusters of galaxies have also shaped the rise of consciousness capable of reflecting upon them. It is easy to see the CMB as distant and indifferent, but in another sense, it is profoundly personal. For without it, there would be no galaxies, no stars, no Earth, no mind to ask what it means. The whisper is therefore a reminder of belonging, that the human story is inseparable from the cosmic story, that to listen to the universe is also to listen to oneself, and yet there is unease. The whisper reveals that 95% of the universe is unseen, that its fate is governed by forces not yet understood, that the truths uncovered so far may only be fragments of a deeper reality. It is a reminder of humility, that knowledge, though vast, is still surrounded by mystery, that certainty is fragile, and that every answer will give way to questions that are larger still. This is not a weakness of science, it is its strength. For the whisper is not diminished by being incomplete. It is made powerful by its invitation to listen further, to refine instruments, to sharpen thought, to dream of theories not yet imagined. Perhaps the most haunting message of the CMB is that silence itself is not empty. The universe is quiet, but its quiet is not void. It is layered with whispers, with memories, with faint messages from epochs long gone. In its silence lies presence, history, and story. And so the CMB becomes a symbol of something larger than cosmology. It becomes a lesson in existence itself, that even when all seems dark, all seems cold, the universe still holds memory within it, that silence is not erasure, but remembrance, that the past is never lost, only carried forward in forms too faint for casual eyes to see. At the end, what does the whisper mean for humanity? It means that the universe is not a stranger. It is an ancient parent, telling its first story. It means that human beings are not separate from the cosmos, but written into it, inscribed in its earliest light. It means that every discovery is also an act of listening, and that listening is endless. Perhaps the universe never stops whispering. Perhaps the silence is only an illusion born of limited ears. Perhaps, in every ripple of light, in every vibration of space-time, in every particle that slips unnoticed through the earth, the cosmos is speaking still. And perhaps humanity has only just begun to learn how to hear. The whisper of the CMB is not only about where the universe has come from, it is about what it means to exist in a universe that remembers. It is about the strange beauty of being part of a story so immense that it can never be fully told. And it is about the possibility that the cosmos, in its quiet persistence, will always have more to say. In the end, the whisper means this: that existence is never silent, that every moment carries the echo of the first moment, that the universe is both mystery and memory, both silence and story, and that to live within it is to live within a whisper that has never ceased and never will. The cosmic microwave background is the oldest whisper in the universe, carrying the memory of creation across billions of years. Its faint ripples map the birth of galaxies, the unseen forces of dark matter and dark energy, and the very rhythm of time itself. We have learned to listen, to trace its echoes, to glimpse the universe's earliest secrets. And yet, the whisper continues, reminding us that the cosmos remembers, that existence carries memory and story. Perhaps the greatest truth is this: the universe never stops speaking, it is we who are learning how to hear. In listening, we discover not only the cosmos, but our own place within it.